Hi, my name is John Fiorenza. I'm a design engineer in the signal conditioning group. Let's talk about the importance of using good resistors along with your op-amp circuits. First, a quick review of the basics. Op-amps are almost always used together with resistors to apply feedback. An inverting gain circuit is shown here, with a positive input of the op-amp grounded. The high open loop gain of the op-amp makes it so that the negative input of the op-amp also stays at ground, and any current that flows through the input resistor must also flow through the output resistor. This creates a ratio between output voltage and input voltage equal to the resistor ratio, which gives us an inverting gain of RF divided by RG. You can see that if the ratio of the feedback resistors is not exactly what you plan it to be, then the gain of the circuit will be off. Typical discrete resistors come in 1% accuracy grades, with 0.1% also available. If that's not good enough, then integrated resistors can give you up to several orders of magnitude better performance. Some systems try to correct for gain error by doing a calibration. That works, but now you have to worry about how the resistor ratio will change with temperature. If you put all the resistors on the same die, they will also track extremely well with temperature. We have achieved gain error temperature drift of less than 1 part per million per degree C. For an op-amp in non-inverting gain, the configuration and gain equation is slightly different, but the same considerations apply. Again, resistor mismatch causes gain error. A difference amplifier configuration is a superposition of the inverting and non-inverting circuits. We now have 4 feedback resistors, and the output voltage is a function of just the difference between the 2 inputs, regardless of the absolute value of any input taken on its own. Here again, the gain accuracy of the circuit depends on the accuracy of the feedback resistors. This was all pretty basic so far, but a difference amp circuit actually has another sensitivity to resistor error, which is not as well known, but can actually be more serious than gain error. It's called common mode error, or common mode rejection ratio, CMRR. Ideally, the difference amp only measures the difference between the input voltages without regards to the common mode or average value of the 2 inputs. So if the inputs are tied together, the output should be 0 even if we move both inputs up and down together. In reality, though, if the resistors mismatch, the circuit will create an unwanted offset error that is proportional to the common mode input voltage. For example, let's say that you want to measure a small difference between 2 inputs, but the combined or common mode inputs can move up and down between plus 10 and minus 10 volts. If you use standard 1% resistors in this circuit, then this resistor mismatch can cause up to 100 millivolts of offset error. This is, of course, much worse than the offset of the op-amp itself. And this offset error changes depending on the common mode input voltage. Since at the output of the circuit you don't know what the common mode input voltage is, you cannot really calibrate for this kind of error. So it can be a real problem, and that's why, especially in difference amp circuits, you often need something more accurate than what you can do with external resistors. Now let me show some specific examples. The LT1997-1 combines an op-amp with a set of precision feedback resistors all on the same die. It is meant to be used as a difference amplifier. Depending on which set of pins you connect to the source, you can select gains of 10, 20, or 50. This can be useful in a current sense circuit, where you want to measure the current that flows through a small sense resistor. You want the output voltage to be just a gained-up version of the differential voltage across the sense resistor, regardless of what the actual voltage is on any of the pins by themselves. That's why you need a good common mode rejection ratio, which you can only get by using very accurately matched resistors. The op-amp that we put inside this chip has an input stage which is unusually flexible and rugged. It allows the op-amp input nodes to operate at voltages even higher than the supply voltage, a feature which we call over-the-top operation. The op-amp inputs also operate at voltages down to the negative supply and are protected to voltages well below it. The result is that the absolute voltages that you can put at the resistor inputs to the circuit can be quite high, up to 84 volts depending on the supply rails applied to the op-amp. The LT1997-2 is a version of this product that is set up for attenuation rather than gain. Depending on which pins you select, you can get attenuation of 0.1, 0.2, or 0.25. This proves particularly useful when your circuit expects large input signals and you need to adapt them to digitize with a low voltage ADC. For example, the circuit shown here takes a plus and minus 10 volt input signal and then attenuates it for an ADC with a 5 volt voltage reference. The op-amp inside the LT1997 features a rail-to-rail output stage. This means that the output signal can swing quite close to either supply rail with good performance. In the circuit shown, we take advantage of that by powering the LT1997 from a single 5 volt supply, which then also protects the ADC from ever being driven into overrange. In this example, the ADC full-scale range is defined by a precision voltage reference, the LT6657, which features a maximum temperature drift of 1.5 parts per million per degree C. If you think about it for a minute, you realize that the temperature drift of resistors in a circuit has the exact same effect on the signal as temperature drift of the voltage reference. That means that the only way to take advantage of the great temperature stability of a high-quality voltage reference is by using precision-match resistors, such as offered inside the LT1997. If you would build the same circuit with off-the-shelf external resistors, then the gain accuracy of the circuit would be completely dominated by the resistors, no matter how good a voltage reference you use. Note that we made a small modification to a traditional difference amp circuit as it relates to the ref pin. Traditionally, there is just one ref pin, which you should drive with a voltage level that corresponds to the output voltage that you want when the differential inputs are 0. To maintain good CMRR of the circuit, that connection needs to be very low impedance, which can sometimes require an additional op-amp buffer or a dedicated voltage reference. But if you just want to bias the output at a level in the middle of the full-scale range of some master voltage reference, it can be more convenient to use a resistor divider from that voltage reference. That's what the built-in resistors between these two ref pins allow you to do. These resistors are matched and trimmed along with the other resistors on the chip, so that full specified performance is maintained. The final version of this family is the LT1997-3. It is designed to be very general purpose, with resistors built in for ratios of 1, 3, and 9. This proves to be very versatile, as you can use it for a wide variety of gains, attenuations, and in both inverting, non-inverting, or difference amplifier configurations. Some examples of the versatility of the LT1997-3 are shown here. You can use it as the difference amp portion of an instrumentation amplifier. Here we use the LT6018 precision op-amp configured in gain and the LT1997 as a gain of 1 difference amplifier to get the very high common mode rejection. Even though the built-in gains are 1, 3, and 9, you can combine resistor inputs to make other gains. For example, if you cross-couple the gain of 1 and the gain of 3 inputs, you actually subtract the 2 gains to make a gain of 2 circuit. Finally, you don't have to use this part in just difference amps. The datasheet shows many examples of how you can use it as a traditional inverting or non-inverting op-amp, while still taking advantage of the excellent matching accuracy of the on-chip resistors. In conclusion, the accuracy of analog circuits is often as much dominated by the resistors as it is by the op-amps or the voltage reference. The LT1997 is a family of products that starts with a precision op-amp with very flexible input and output stages and adds a wide variety of precision match resistors. This allows you to build op-amp circuits with excellent gain accuracy and to preserve the performance of a high-quality voltage reference. It also avoids offset errors due to variation of the input common mode voltage. For more information, please check our website. Thanks for watching.